Welcome back to this first course in general physics. Now we will be discussing the motion of a single particle. We will be concerned with only the description of the motion without regard to the causes of the motion. In this chapter 2 of this course, we will be focusing on the branch of science that we call kinematics. We will be discussing kinematics of a single particle. So, the outline of this chapter would be the motion of a particle along a straight line as the first part of the description of motion of a particle. And in this regard, we will define the parameters which are necessary to describe the motion, namely the position and displacement of the particle, the average velocity, the instantaneous velocity, the speed, the acceleration, both the average and instantaneous. And then we will move to discuss the motion of a particle having a constant acceleration as a special case. We will take a special case, the free falling bodies, the motion under the influence of gravity. And in the second part of this chapter, we will be discussing the motion of a particle in 2 or 3 dimensions, in 3-dimensional space in general. Also, here we will define the position and displacement of the particle in 2 and 3 dimensions. We will define the velocity and the acceleration. And after we have defined these parameters, which are necessary for the description of motion, we will take a special case and we will study the motion of a projectile, an object under the influence of gravity, projected with a certain speed, initial speed. And for the projectile, we will derive from the motion certain parameters such as the equation of the path for the projectile. How does the trajectory look like? And from the trajectory and from the motion, we will calculate the maximum height at which the projectile can reach, and then we will be able to calculate the range of the projectile. How far horizontally does it go? As we know, everything in the universe is in constant perpetual motion. Everything moves. Even the objects that seem to be stationary do move. The streets, the trees, forests, the houses that we live in, all move with the motion of Earth. The Earth moves around the sun moves around a certain spot in the galaxy, and the galaxies travel. If we go into a smaller scale, a solid, an object, consists of atoms. These atoms are in continuous vibration, motion. The atoms contain electrons and protons inside the nucleus. The electrons are in constant motion around the nucleus. And the protons inside the nucleus are in constant motion also. Everything moves. So, what is the definition of this branch of science that deals with the description of motion? If we are involved only in the description of such motions, then we are talking about what we call kinematics. Kinematics is the branch of science that deals with only the classification and description of the motion. What do we need? What do we need? What do we mean by the description of motion is to identify whether the object is stationary or moving. If it is moving, how fast it is moving. Is it changing how fast it is moving? Does it move in a certain direction and keeps that direction of motion? Does it change that direction of motion? All of that is involved in what we call the description of motion, or this branch which we call kinematics. Thus, we realize that the motion of an object can be along a straight line in one dimension, and this motion is the simplest motion of an object. So in that sense, we will be considering this type of motion as our first example to illustrate and to discuss. So in this part, we will discuss the motion along a straight line. In this sense, we will be discussing the motion of a single particle in order to be able to define a spot, a point that locates the particle. Also, motion of a single particle would represent the motion of an extended body, an object with dimensions, but under the condition that every part of that object is moving in exactly the same way, the same speed, the same velocity, the same acceleration, and the same direction. If every part of the object is moving in exactly the same way, then we can consider the motion of that object to be simulated by the motion of a single particle. The particle that represents the object can be any particle in it. It doesn't matter because every point in the object is moving in the same way. A convenient choice for a point that represents the object is the center of the object. Now, when we talk about the motion and the description of motion, what do we mean? Motion involves the position of the particle. when we say a particle moves, that means it changes its position. It changes its position from an initial point to another point. And that change in position involves the motion of the particle. So position is one of the parameters that we are concerned with in describing the motion of a particle. What are the parameters that we need in order to describe the motion of a particle? When we speak of the motion and we say we want to classify the motions, we want to compare the motions, we want to describe the motions. In order to describe and to compare and to classify, we have to rely upon some parameters. And what are those parameters that are involved in the description of the motion? One of the parameters should be the velocity, how fast and in which direction does the particle move. That would be one useful parameter that describes the motion. The other parameter which is useful in the description of the motion of a particle is the acceleration, which involves the concept whether how fast it is changing in either the magnitude, does it become faster or slower, or in direction. Both changes are involved in the concept of acceleration. So acceleration also is an important factor in describing the motion of a particle. How do we define the position of a particle? As we might think, we have to locate, first of all, a point, a reference point, relative to which we can measure the position of the particle. That reference point is called the origin, O. And from that origin, we draw an arrow, a vector, that starts from the origin to the location of the particle, and that vector represents the position of the particle. The length of the vector is associated with the magnitude of the position, meaning how distant it is from the origin, and the direction of the vector would represent the direction of the position of the particle. So the position is a vector that involves both magnitude and direction and is measured relative to the reference point, which is the origin, we call the origin. When we discuss motion along a straight line, we are dealing only with two possibilities for the direction. If we consider, for example, the x-axis, the horizontal axis, then the directions involved are only right and left. We don't have any other choice. So how do we define the direction in that sense? In this case of the motion of a single particle along a straight line, we define the positive direction as being the direction in which the coordinate increases. And it is, if we consider the x-axis, we usually consider the right-hand side as being the positive. So if the particle is moving right towards the right, then we say it is moving and increasing the position, and the position is positive. and the change in the position is positive if it is moving right, and vice versa. If it's moving left, then the change in the position is being negative. And if we consider the motion along a straight line which goes up and down, we consider the upward direction as being positive and the downward direction as being negative. This is just a definition. In the motion, as we mentioned, we encounter the change in the position of a particle. This change in position of a particle is called the displacement. So when a particle moves from one point at a location x1 to another point located at x2, the difference between these two locations or positions is called the displacement. The displacement is symbolized by delta x, which is equal to x2 minus x1. That is the final position minus the initial position. That is the displacement, which is the change in position of a particle. This displacement is also a vector because it is the difference between two vectors, which are the initial position and the final position. The position is a vector, then the difference in position would also be a vector. The displacement is thus a vector. If the result of x2 minus x1 is positive, then we say that the displacement is positive. That means the displacement is towards the right if we are concerned with the motion along the x-axis. Or if we are concerned with the motion up and down, then if delta x, we call it in that case delta y, just to differentiate between the two motions. Then if the displacement is positive, then we say that the particle is moving upward. Now we are at a point where we can define some of the parameters of the motion. One of them is the velocity. How fast is the particle moving and in which direction? The velocity is a vector. It involves a magnitude, how fast, and a direction. In which direction is the particle moving? In the beginning, we define the average velocity. If a particle moves from one location to another during a period of time, delta t, between an initial time t1 and a final time t2, if the initial position at time t1 is x1 and the final position at time t2 is equal to x2, then the average velocity is defined as v with a bar over it, meaning average, is equal to delta x over delta t, where delta x is the displacement, x2 minus x1, and delta t is the time interval of the motion, t2 minus t1. This defines the average velocity, and as we notice, the average velocity is also a vector that involves direction as well as magnitude, because the displacement delta x is a vector and delta t is not a vector, is a scalar. So the average velocity would be the product of the displacement and 1 over t, 1 over delta t. The sign of the velocity indicates its direction, and that sign is exactly, or direction is exactly the same as the sign or direction of the displacement, since the average velocity is derived by dividing the displacement by a scalar delta t. If we plot the position on the vertical coordinate x in meters versus the time on the abscissa or the horizontal coordinate, and if we consider this bright blue trajectory, which defines the motion of the particle with time, the change in its position with time, then the average velocity is simply the slope of the straight line connecting the point at the initial time and the point at the final time. Between the point or the location at the initial time and the location at the final time for the motion, between these 2 points we draw a straight line, and the slope of the straight line, which is delta x, the vertical displacement, over delta t, which is the time interval, that slope, delta x divided by delta t, is the average velocity of the particle. That is a graphical representation of the average velocity of the particle. If we are concerned with the instantaneous velocity, which means how fast is the particle moving and in which direction it is moving at a specific point in time, if we are concerned with this question, so what do we do? Previously, we have defined the average velocity. We have described how to calculate the average velocity, which is the velocity during a period of time, an extended period of time. In order to find the instantaneous velocity, the velocity at a given time, all that we need to do is to use the same definition previously used to calculate the average velocity, and to shorten the time interval for the motion, delta t, shorten it and take it smaller and smaller and smaller until it becomes 0. It goes to 0 at the time of interest, where we are interested in measuring the velocity of the particle. So that instantaneous velocity, which is the velocity at time t1, say, can be obtained by taking time t2, the final time for the motion, during the interval of the motion, t2, taking it closer and closer to time t1, the initial motion, until delta t goes to 0, and then the displacement traveled in that period of time, which goes to 0, it is infinitesimally small. The ratio between the distance traveled during that period of time, very small period of time, to the period of time, divided by the period of time, is the so-called the instantaneous velocity at that time of interest. So mathematically, this is described as velocity, the instantaneous velocity, or the velocity, we can call it, is simply the limit of the average velocity, delta x over delta t, as delta t goes to 0. This definition, limit delta x over delta t as delta t goes to 0, is simply the derivative of the position x with respect to time, dx by dt. That means the average velocity of a particle can be calculated directly if we know how does the position of the particle change with time. That is, if we know the position as a function of time, then we can evaluate the instantaneous velocity of that particle by simply taking the derivative of that position as a function of time with respect to time. Deriving x with respect to time would give the instantaneous velocity. How does this look on an xt curve? Again, if we plot the position of the particle x on the vertical scale and the time it takes for the motion on the horizontal scale, and the light blue curve represents the motion, which is the change in position with time, then the instantaneous velocity of the particle at a given time, the time of interest is here described by the dashed line downward. At that point in time, the instantaneous velocity is simply the tangent to the curve, to the xt curve at that point. So if we have the position of the particle as a function of time on a graph, then we can evaluate the instantaneous velocity at any point in time by taking simply the tangent to the curve at that point in time. Sometimes we are concerned with another parameter which is called the speed. The speed is simply how fast is the particle going without regard to the direction. The average speed is thus defined as the total distance traveled by the particle divided by the time it takes the particle to travel that distance. So simply, if we are concerned with calculating the average speed of a car, for example, traveling between Torino and Rome, all that we have to do is to calculate the total distance traveled by the car and the time it takes for that trip, and divide that distance by the time, and that would give us the average speed of the car during that period of time. This is the definition of the average speed. And if we would like to know the speed of a particle at a given time, instant in time, then it is simply the magnitude of the instantaneous velocity at that instant in time. So we simply evaluate the velocity, which involves magnitude and direction. And if we take only the magnitude, that represents the speed of the particle at that point in time. The second parameter, which is required for the description of the motion, is the acceleration. If the velocity of a particle changes from time to time, then we encounter what we call the acceleration. We say that the particle is accelerated. Thus, during a time interval delta t extending from t1 to t2, if the particle's velocity changes from v1 to v2, the average acceleration of the particle during this period of time is defined as a bar, which means average acceleration, is equal to delta v over delta t, where delta v is the change in velocity v2 minus v1, and delta t is the interval of time during which the motion took place, t2 minus t1. And graphically, if the velocity is plotted on the vertical scale with time on the horizontal scale, then the straight line in green here between t1 and t2 connects the 2 points in time during which the motion took place. So between t1 and t2, that straight line extending between the point at t1 and the point at t2, the slope of that straight line is simply the average acceleration of the particle during the time delta t. If we are concerned with the instantaneous acceleration, which is the acceleration of a particle at a specific point in time, how fast and in which direction is the particle moving at a given point in time, then what we do is exactly similar to what we have done in evaluating the instantaneous velocity. We take a period of time for the motion delta t between t1 and t2, and then we take t2 closer to t1. We shorten the period of the motion until t2 goes almost exactly to t1, where delta t goes to 0. And then we take the change in the velocity during this period of time delta t where it goes to 0. The average acceleration is then the average acceleration is delta v over delta t. If we take the limit as delta t goes to 0, then the instantaneous acceleration is the limit of delta v over delta t as delta t goes to 0, which is the derivative of v with respect to t. Then that means the acceleration, the instantaneous acceleration, or simply the acceleration, is the derivative of the velocity with respect to time. So if we also remember that the velocity itself is the derivative, first derivative of the position x with respect to time, then the acceleration is the derivative of the derivative of the position with respect to time, which we call the second derivative of the position with respect to time. That gives us two alternatives for the evaluation of the acceleration, which is one of them is simply the derivative of the velocity with respect to time. So if we know the velocity, how it changes with time, the velocity as a function of time, its derivative is simply the acceleration, or vice versa. If we know the position as a function of time, then the second derivative of the position with respect to time gives us the instantaneous acceleration. As a special case, we consider the motion with a constant acceleration, and we remember that we are considering the motion along a straight line. We still are in that region of the description of motion. In this case, if the acceleration is constant, then the instantaneous acceleration A is exactly equal to the average acceleration. That's what we mean by constant acceleration. The average acceleration, which is delta V over delta T, is equal to the instantaneous acceleration A. So we write A is equal to V2 minus V1 over T2 minus T1. Acceleration is equal to the average acceleration. From this definition, for the constant acceleration, we can arrive at the equations of motion. But before that, we have to remember that also, if we have a constant acceleration, then the velocity of the particle is changing linearly with time, uniformly with time, which means we can define the average velocity of the particle during the interval of motion as being half of velocity at time 1 plus velocity at time 2. So the average velocity is half of V1 plus V2. That is a consequence of the motion with a constant acceleration. So we have now these two equations that we can use to define the motion of a particle. But also, we have to remember that in defining the motion of the particle, we have 5 different parameters for the motion. These 5 parameters are the displacement x2 minus x1, the velocity v1, the velocity v2, the acceleration, and the time interval t2 minus t1. Thus, if we can find 5 equations, each one of them containing one of these 5 parameters as an unknown, where the rest of the parameters are known, we can have a way of solving any problem and finding the unknown parameters of the motion. If we, for simplicity, set T1 equals 0, T2 equals T, V1 equals V naught, V2 equals V, then from the definition of the average acceleration, we have this equation, V equals V naught plus AT. This is coming from the average acceleration. From the definition of the average velocity, we have x minus x naught over t, which is simply delta x over delta t, is equal to v naught plus v over 2. This is from the definition of the average velocity, and this gives us the second equation of motion, delta x, which is equal to x minus x naught, is equal to 1/2 v plus v naught into t. The remaining three equations of motion can be found by simply eliminating one of the three common parameters between these two equations at a time. Notice that these two equations we just derived have three common parameters between them, which is, one of them is the final velocity v, one of them is the initial velocity v naught, and the third common parameter is simply time t. So if we eliminate v, for example, between these two equations, we get a third equation which does not contain v, but rather it contains the displacement, the velocity v naught, the acceleration a and t. And if we replace v naught from the second equation, if we substitute for v naught, similarly we get a fourth equation. And if we substitute from the second equation for t into the first equation, then we get the fifth equation, which does not include t in it. And this way we get the five equations of motion. One of them is, the first one is the one that we derived from the acceleration, the definition of the acceleration. And the second one is from the definition of the average velocity. The third one is obtained by substituting for v in between these two equations. This one is obtained by eliminating v naught from the two equations. And this final equation, v square equals v naught square plus 2a delta x, is obtained by eliminating the time between the two first equations. Thus, we get five different equations of motion for the particle. We can locate which equation to use by simply deciding what do we want to know, what is required, and what are the parameters that are known. And that way we select the right equation and we solve the problem and we find the unknown parameter. At this point, I would like to finish this lecture and thank you for your attention.